Good morning, everyone. So today we will continue our discussion on geometrical isomerism. So we started with the definition of geometrical isomerism, and we tried to see certain examples. So in your syllabus, you have two molecules that you have to study, their geometrical isomerism. So butene and butene 1,4-dioic acid. Both these examples we have seen in the last class. So this particular example is your cis isomer, and this is the corresponding trans isomer. Okay, so these things we have done already in our previous classes. So in both these cases, the cis isomer I have drawn on the first, and the trans isomer I have drawn the second one. So if you look at this molecule, you are pretty now sure how to draw a cis and the trans isomer for these two compounds. So this I have already told you that the cis form is called by a common name like Maleic acid, and a trans form is called as the Fumaric acid. So these things I have discussed before in the previous video. So right now, what we are going to discuss in today's class is that we are going to see how we can distinguish the various geometrical isomers on the basis of their melting point. Okay, so how we are going to distinguish the various geometrical isomerism on the basis of their melting point or on the basis of their dipole moment. So let's first look at the melting point. Okay, so for these two isomers, I am going to show you the melting points of these two compounds. So here, let's look at the first compound. So first compound, the melting point of cis isomer is minus 138 degrees centigrade. However, for a trans isomer, it is minus 100.5 degree centigrade. So here, what do you see? The trans isomer is having a higher melting point compared to a cis isomer. Similar to that, if you look at the maleic acid and you compare it with the fumaric acid, what you see? The fumaric acid, which is the trans isomer, is having a higher melting point compared to maleic acid. Now, in both these isomers, trans isomer of both 2-butene and 2-butene 1,4-dioic acid, in both cases, you see a higher melting point in the case of trans isomer. Now, you would ask me, now why that is so? The reason for why trans isomer is showing a higher melting point is because of the packing in the solid state. So in the solid states, when the isomer is in a trans form, they kind of pack well. I mean to say, usually if you see a trans isomer, what you see here is that the trans isomer is kind of zigzag. Okay, if you look at this molecule, the trans isomer can be drawn in a zigzag fashion. However, the cis isomer doesn't have a zigzag conformation, but rather it is a boat-like conformation. So that is why in trans isomer, when it is in the solid state, there is better packing between the molecules, and because of that better packing, they have better interactions, be it van der Waals or be it other kinds of intermolecular interactions. They are kind of enhanced when they are in the trans conformation. So as a result of that, what happens? The melting point will increase. Obviously, when their intermolecular interaction between the molecules becomes significant, then it would enhance the melting point of the molecule. So that is why you see enhanced melting point when you see the trans isomer. So this is one way of kind of finding the melting point the boiling on the basis of melting point, you can distinguish a cis and a trans isomer. So usually trans isomer will be having a higher melting point than the cis isomer. Now why it is so? Because of the better packing of the trans molecule in the solid state, because they are more symmetrical in their solid state, and in the trans form they have better intermolecular interactions. So all these factors together contribute to a higher melting point of the trans isomer. Now, another thing that we are going to see right now is the distinguishing between the cis and trans isomer on the basis of the dipole moment. Okay, dipole moment can also kind of determine the distinction between a cis and a trans isomer. Let's look at one of the examples. So here we have the example of 2-butene. So cis isomer, if you see, there is a kind of dipole moment which is acting in this fashion. Similarly, you have a dipole moment which is acting in this particular fashion. So both the dipoles are acting in the same direction. Okay, so they will have a net dipole moment in one particular direction, and therefore it will have a net dipole moment. So in case of cis isomer of but2e, you will have a particular value for the dipole moment. So in this case, it is 0.33 d. Okay. Similarly, but if you see the trans isomer, the dipole moments would be kind of cancelling out each other, because one of the dipole moment is directed in the upward direction and another of the dipole moment is directed in the downward direction. So net effect is both these will cancel out each other. So the net dipole moment would be 0. Okay. So dipole moment arises, as you know, because of the kind of charge, a partial charge that is developed on the bonds as a result of difference in electronegativity. So it is electronegative because it's, if you see this bond, this is more electronegative than a sp3. So the direction of dipole moment would be something like this. Okay, so this is how you will find out you come to know that cis isomer will usually have a net dipole moment in comparison to a trans isomer. I tried to check the dipole moment for the fumaric and Maleic acid, but I couldn't find exactly the values, so I did not write them down. So if you see these two molecules, I believe that they will have a similar effect. The cis isomer will be having a higher dipole moment in comparison to the trans isomer. But one thing I found in the case of fumaric acid is that they do not have a zero dipole moment, but rather they have some dipole moment, but it would definitely be lesser than the dipole moment for a Maleic acid because of their cis conformation. Okay. Now we have few other examples of which we are sure about the dipole moment. So here I have 1,2-dibromoethene, which I have drawn in both cis conformation as well as in the trans conformation. So what do you see in the cis conformation? If you see the direction of dipole, it would be something like this. Okay. Similarly, you will have the direction of dipole happening in this particular direction. Okay. So they will all have a net dipole moment in one direction. Similarly, you will have the dipole moment directed in this particular fashion. Okay, so in both these cases, what do you see? We have both in the 1,2-dibromo as well as 1,2-dichloro, you have a net dipole moment and they have a particular value. However, when they are in the trans conformation, in the case of both dibromo and dichloro, what do you see? The net dipole moment is kind of 0. Okay, because the dipoles are acting in the opposite direction. So somehow they cancel out, and therefore the net dipole moment would be a zero value, would be a zero value. So this is how you can talk about the, you can see that both melting point as well as the dipole moment can be used as a kind of property on the basis of which you can distinguish between a cis and a trans isomer. So when we talk about melting point, when it is a trans isomer, you will have a higher melting point compared to a cis isomer. And when you talk about a dipole moment, the cis isomer would be having a higher dipole moment compared to a trans isomer. So now you're pretty able to understand the various factors that are kind of influencing factors or the property on the basis of which we can distinguish between a cis and a trans isomer. So these are the true properties only mentioned in your syllabus. So I have discussed only those two. There are other factors like solubility also. You can take it as a property to distinguish between cis and a trans isomer. Apart from that, in the case of Maleic acid and Fumaric acid, you can distinguish them on the basis of formation of anhydrides. Okay. And then on the basis of heat of hydrogenation also, you can distinguish between cis and trans isomer. So I'm not discussing all those things because being in the complementary, you have only two properties that on the basis of which you can distinguish the cis and the trans isomer that you have to study. So I'm not complicating the thing. So I hope you understood what I have discussed so far. And any doubts you can ask me. So with this, I would like to wind up geometrical isomerism. We will be going in the next class with the conformational isomerism. So thank you very much. God bless you.